environment. So first off, how's everybody doing today? I need to wake up a little bit. Is it warm in there?
I'm doing great. I'm great. How are you guys? You guys great?
Yeah.
Woo! Come on! Come on!
I'm not going to subject you to tons of PowerPoints today. We're going to be able to get up and get moving. But we do have to go over a few things. How many of you use water? Okay, so you pretty much all use water, right? It's pretty important to you. If you didn't have water, what would happen? You'd die. So basically, we're going to go with that. So I want to know how you use water. So with the two post-its behind you, please put down two different ways, one on each paper, of how you use water. I'll give you about 1 minute, because we want to tell you everything there is to know about water. I don't think we can use it on, so hopefully it'll pop out soon. Yeah. Okay. Is anyone else without post-its? Apparently you guys are still asleep and I asked that like 5 seconds ago. There you go. Everybody tell me how to get their ideas on paper? 2 ways to use water? Alright, so does anyone want to share with me one of their ways they use water? Yes, drinking. Drinking! Excellent. I'll come get that. Does anybody else have drinking water? Oh, wow. You guys all drink water? Good job. Very, very good. Yeah, great minds think alike. Wow. Look at this. So who else drinks water? Awesome. We are made up of 70-something%. It's the healthiest thing you can do. All right. All right, so there's a whole bunch of us that drink water. All right, so can somebody else give me an idea? Oh, sorry. Does anyone else have anything else that they do with water? Yes. Recreation. Recreation, like what kind of recreation? Swimming. Excellent. Well, we will go under recreation. Maureen, would you mind grabbing somebody else? So, and who else has recreation? Who else uses water for recreation? All right, excellent. So hand those over to Maureen. Thank you. Anybody else? Anybody else? That's a big old lake right there. All right, no, recreation. All right, what are some other uses? Yes, cleaning, like showering. Cleaning, bathing. Excellent. Does anyone else? Oh, thank God, you guys all bathe. Not everybody. Drinking okay. All right, so everybody drinks water. All right, what else do we use it for? Yeah, cleaning Oh, excellent. What did this gentleman just say? Those that were talking over there? Can you repeat it one more time? Hydroelectricity. So does anyone else have it as a use for powering it? Excellent. All right, so we got recreation, drinking, shower. All right, what else do we have? Yeah? Plumbing and waste removal. Okay, so we'll put this in drinking. Does anyone else have plumbing, waste removal, flushing the toilet? I can take that. Thank you. All right, what other thing? How else do we use water? Yes.
Cooling our bodies in the form of sweat.
Oh, cooling our bodies in the form of sweat. So, does anyone have? I like that word. It's been a long time since I've heard it. So excellent. So, as a natural coolant. Awesome. Yes, how else do you use water?
Dissolve solids so that you can nice and move and react.
Oh, dissolve solids, and that's really important, especially if you want to drink tea, right? You throw some sugar in there, throw some water in there. Who wants to drink a thing of sugar, right? So it's kind of important for, not just that's one of the simpler things, but it's a universal solid. So, excellent. All right, what else? Yeah.
Food production.
Food production. Very good.
Agriculture, right?
Agriculture. Does anyone else have familiarity in agriculture? All right, any other ideas or any other uses? Yes.
Aquaculture.
Agriculture. Excellent. So we can go, they usually group that with agriculture, so we go agriculture, agriculture. So, I don't know where I put my markers. So anyway, there's a couple of different ways that we use water, and they are actually competing sources. So we use it to drink, we use it to clean, we use it for recreation, there's to dissolve solids, we use it for just, well, basically, let's do this. So, all right, we use it for washing. We use it for, for waste removal, and we use it to grow food, agriculture. So basically, there's a lot of competing uses for these resources, right? There's a lot. So what happens if brother's in the shower, mom decides to flush the toilet? It's a competing resource. So this is similar. So not only do we use it for all of this, on top of that is there's two different types of water. We have salt water and fresh water, right? What kinds of water requires drinking? Fresh water, okay? Recreation. You can go both, right? So salt water, fresh water. All right, what's the best to dissolve solids in for food preparation and stuff? Fresh water. How about cleaning? You're cleaning yourself. What kind of water are you using? Fresh water. You don't want all that salt on you. Hydroelectric power, more than likely would be what?
Fresh water.
Fresh water. You probably could do a little bit with salt water, but mainly we're talking about dams and rivers where you're harnessing the river energy. And then we have growing food. What are we talking with that? Salt water, fresh water? Fresh water. Or aquaculture. Or aquaculture, you're right. Yes, aquaculture can go both ways. For cooling your body, same thing as pretty much. But mainly we need fresh water, right? Can anybody tell me how much fresh water is available for us, which is called potable, that's for drinking and bathing and stuff like that? How much water overall in all the water in the world? Yes.
Wait, 1%? Because a lot of it's ice.
A lot of it's ice. So you have pretty much 96% of the water is, 96.5% is ocean, 3.5 is fresh water, then you have ice caps and stuff like that. So pretty much less than 1% is actually potable where you can drink it. The other problem that we have with fresh water, with all the demands on fresh water, is the fact that we are recycling the same water that the dinosaurs used through the water cycle, and Maureen's actually going to be going right into that. So we're pretty much competing for those resources, and if we don't turn around, so whatever we use, if we're polluting that water, that gets taken out of that potable usage. Also, if you probably don't even think about this, but if you throw away water in one of those plastic bottles, can anybody tell me how long it takes for a plastic bottle to deteriorate? Yeah. A long, long time. So before, like water in one, I'm going to use this, right? When one of these bottles actually gets back into the system, it's going to take thousands upon thousands of years. Yes.
won't never deteriorate because we're basically forming giant vacuums in our, like the Johnson landfills, when we basically a giant time capsule, so it doesn't have any of the bacteria or air to deteriorate ever.
I was going to turn around and be a little more positive, but yes. You are out of surprise. I was trying to avoid doing a little bit. Okay, yep, you have a point. We keep putting it in, you turn around and you're like burying that stuff in the garbage, it won't break down. All right, so now on that high note.
There's also the giant Pacific garbage patch.
Yes, I actually saw pictures of that. But as soon as I saw that, I would never drink plastic water bottles. As I pick up the case of water bottles for my kids for soccer, and I feel so guilty now doing that because I look and there's just like all these water bottles floating in the Pacific Ocean, this huge garbage heap.
There's a great mockumentary called "The Majestic Plastic Bag" from California. It's all about the life cycle of a plastic bag.
Nice. Well, and also the problem with plastic bags is the fact that they will put jellyfish in there, or animals out in the ocean that actually eat the jellyfish that are eating plastic bags instead. You're not getting any nutrients and stuff. But anyway, we are on a tight schedule, so I'm handing it off to Maureen. She's going to talk about water cycle and all sorts of stuff that we will need you to know for your test.
Woohoo, test time.
Okay, good morning everyone. Thanks for having me here today. It's really cool to be in the midst of, environmentally minded youth, the next generation who's going to fix all of our lovely problems, right? Civic garbage patches and things like that. So I just have a handful of slides. I don't like to do PowerPoints for the most part. I'd rather be hands-on and do some other activities, but some of these things are just easier to visualize, and while we were going to make you do an interpretive dance to do the water cycle, we thought it might be just a little too early on a Saturday, moderately embarrassing. So I don't want to do that in front of you, and I'll spare you the same. So I'm sure some of this that I'm going to cover is probably stuff you've covered in your science classes already, so pardon me if this is really basic, and feel free to speak up if you want to add anything or you have anything to share. Or if I miss anything major. It's been a long time since I've studied the water cycle, to be perfectly honest. But we did want to cover some of these really basic things just to make sure we're all on the same page and that you guys can ace the test, okay? So this is about as basic as the water cycle gets, right? There's really no beginning and no end. And as Kim just previously said, the water cycle, it's been ongoing for billions of years, literally. It's pretty much the same water. So if we let's start in the ocean. You've got all that ocean water, lake, stream, river water. It's evaporating. Water vapor is also being put back into the air through transpiration from plants. So you've got evaporation happening, vapor goes into the air, gets cooled, condenses, you get cloud formation. What happens when you've got the clouds, the particles colliding? You get precipitation in the form of snow, rain, whatever, sleet. Falls down. The majority of that is going right back into those water bodies, primarily the oceans, just because it covers so much of the globe. It is also the precipitation is also contributing to surface runoff, so anywhere it's hitting land or parking lots or roads or whatever, it's running down over the land, over urban areas, and taking anything with it that's in its way and bringing it back into the water, into the streams as well. The other place that water is going is into the ground as groundwater. It's refilling our aquifers. So that is really, really basic water cycle. But just knowing those terms and kind of knowing, if you can trace the path of one drop of water, how it's getting up into the atmosphere, how it's coming back down, what avenues it's taking, whether it's falling directly into water, hitting the ground as surface runoff, or potentially permeating the ground and refilling the groundwater and the aquifers. Pretty good? Easy breezy? Okay. Perfect. So, oh no, why isn't it? Okay, there it is. It's delayed reaction. Apparently, I was like, oh. Okay, watersheds. Who's familiar with a watershed? What do you know about watersheds?
Watershed is all of the water from a certain area that will flow back into a body of water. So you work at Narragansett Bay.
I do.
I know that Narrow River has a lot of watershed problems.
Yep.
And so there's a lot of things that they do to fix that. Watershed has problems with nitrogen, pet waste, road salt, things like that.
Yep, perfect. We're going to talk a lot more about that as well in just a bit, so that's a great intro. Watershed to me is one of those really hard things to visualize. Like it's a weird thing to describe, and to me a visual really helps. And so we're going to actually use this watershed model in a little bit. But yeah, watershed is essentially an area of land that drains all of the streams and rainfall to a common outlet. So whether it's a river that then runs into Narragansett Bay, or as this picture shows, any rainfall, any precipitation that's falling in this region is going to eventually make its way into a stream, a river, a brook, and then it'll make its way into a bigger body of water, presumably like Narragansett Bay and then the ocean. And so, let me show you the next slide, I think. So just to give you an idea, this is Narragansett Bay's watershed. And as you can see from this map, what state does the majority of Narragansett Bay's watershed lie in?
Massachusetts.
Yeah, Massachusetts. 60% of Narragansett Bay's watershed is in Massachusetts, and only 40% falls in Rhode Island. So that means we need to be educating everywhere. We need to be educating out of state as well, because almost all the way up to Worcester, if you're familiar with Worcester, Massachusetts, our Narragansett Bay watershed includes up towards Worcester, Massachusetts. That's an awful lot of urban area and runoff that is coming into all these waterways. All the blue are all the streams and the waterways that are eventually going to be making their way into Narragansett Bay. So what does that mean? What kinds of things are going to be impacting Narragansett Bay watershed, even from miles and miles and miles away? What are things we're going to have to be aware of that are impacting that water quality? What do you think?
Nutrient pollution, like fertilizer or chemicals.
Perfect. Yep. New overload of nutrients, right? Nitrogen, phosphorus, fertilizers. Where are fertilizers being placed?
On lawns.
Lawns. Yep. People want a green lawn. Where else? Who else is a big culprit of fertilizers?
Agriculture, pesticides.
Agricultural. Yep. Pesticides. What else? Did you want to say something? Okay. Sorry.
Golf course.
Golf courses. Yeah. Everybody wants a nice, lush, green golf course, right? Oops. It's probably a little bit of fertilizer being put on those. So what happens when it rains?
It washes down.
It's got to go somewhere. It's not just going to sit on the grass. Some of it might soak into the ground, but a lot of that is going to go right into our waterways and just produce excessive amounts of nutrients, which some nutrients are great. They're important. They're needed. But it's when you have an overload of them that they can cause algae blooms and lots of water quality problems. What about... Well, think about Providence and, a lot of these suburban towns. What does the majority of land cover? Is it green grass and forest and trees?
It's roads.
It's roads. It's roads, it's parking lots, it's rooftops. What happens when it rains with those areas?
All the stuff on the roads runs down.
Salt. Yeah, I know there were a couple times this winter when there was really not much of a storm, and there was so much salt on the roads. I thought, oh goodness gracious, there's going to be so much extra salt going into the waterways. All that salt is going to run off. It'll eventually dissolve and be diluted. That's probably not super problematic, but a lot of salt. What else? What else do you see on the roads? Any roadside or any parking lot? Trash? What was that?
It also can't percolate down to this natural soil, so it can't naturally get rid of all those excess nutrients.
Yeah, exactly. If it's hitting pavement, something impermeable, it's going to just go right into the water as that full amount. It's not going to have a time to dissolve and dilute through the groundwater and through the natural processes, like through a wetland or something. Very good. Did you want to add something?
Oil slicks for cars.
Yeah, oil slicks. Yeah, people have leaky oil tanks in their cars or leaky. I don't even know how it leaks out, but clearly I'm not a car person. But they have oil slicks leak out. Any number of things, cigarette butts, all kinds of litter and trash, all that stuff is going to end up in the waterways. So that's just, to me, that's a really powerful image to get your head wrapped around what a watershed is. So if you think about that whole area of land, whenever it rains or snows and all that precipitation is making its way into any one of those little streams, and finally it'll eventually work its way down into one of the major rivers that flows into Narragansett Bay. So while I might work way down here on Prudence Island in the middle of the bay, a lot of the resulting water quality issues we have here that we're studying are coming from much further away. So it's a really much broader issue, and it's important to recognize that. And if I show you back up on this one. So, and just to understand, there are, multiple watersheds, obviously. Everybody lives in a watershed. So in this example here, this ridge line here, any of the water that flows on this side falls into this watershed. If it rains and falls off and starts draining on this side, that would be a different watershed. So there's usually a kind of a dividing ridge area that would designate sort of which watershed it falls in, which direction the water is going to flow down. So, all right, so there's that one. Okay, so obviously when it rains, it's going to fall into the streams, rivers, the bays. It'll hit the ground, act as surface runoff, and fall into those water bodies as well. But some of it is going to recharge our groundwater supply, which is really important. How many of you are on well water at your house? Almost everybody. Yeah, so quite a few of you. So that's coming from one of a couple kinds of different aquifers that we have here in Rhode Island. So aquifers are the water that is underground. And so if you visualize, I have actually a picture that might be good. I'll show you this one first. So you've got all this water that's underground that's really deceiving because you don't even think about it being there, but you've got all this kinds of sediment, gravel, rock that's underground. There's lots of cracks and crevices, and it's all filled with water. So in Rhode Island, there are a couple of different common types of aquifers. There's the sand and gravel aquifer. This one's really common. If you think about digging a hole at the beach and how the water kind of seeps right back in, that's the sand and gravel aquifer. So if the well at your house looks like it's being covered by a manhole, you probably have a sand and gravel type aquifer at your house. So that's a really common one in Rhode Island. The bedrock aquifer is a lot deeper, and if you have like a pipe that sticks up out of the ground as your well pump area, that's probably you have a bedrock aquifer, and that's much deeper through solid rock or something like granite. There are cracks and crevices, and that's where the water is, but those are a lot deeper than the sand and gravel. So these are two common specific types of aquifers that we have here in Rhode Island. One other distinguishing thing about aquifers, I'm going to bring that picture back up. They can be unconfined or confined. And so just those names themselves sort of tell you what that means. The unconfined aquifers generally, it's the one right at the surface, like up to the water table area. So there's nothing limiting it. And so if this unconfined aquifer is the one closer to Earth's surface, do you think it's more or less susceptible to contamination? More susceptible, right? There's nothing to block pollution, oil, waste, chemicals from potentially seeping through and contaminating that groundwater. But when people get really concerned about pollution spills, toxic chemical spills, there's nothing preventing that from going into the groundwater and potentially affecting your drinking water, your aquifer. So unconfined aquifers are closer to the surface. Then there's also a confined aquifer, which means there's a layer of solid bedrock or some other kind of material that is basically impermeable. And it's deeper, and it's basically not going, it will be much less likely to be contaminated in any way, because you've got that solid layer of something confining it. It's a permeable rock, or impermeable rock layer. And so you've got a layer, and then below that you have this confined aquifer, and that water will be much less likely to be impacted or contaminated in any way. Yes?
But also, don't they may never or very slowly recharge over time, so it'd be draining too quickly?
Yeah, really, like the movement of water through it is imperceptible, really. It's very slow. Yep.
And that's actually really important, not to interrupt, but
No.
in Oklahoma, basically they're talking about trying to recharge their underground aquifer because during times of droughts, and basically what's happening is one of their solutions is to actually tap into the confined aquifer and pump water into it. Does anyone see the problem with that?
You're opening it to pollution if it's confined.
Exactly.
Yeah, you just open the door for contamination. So, very good. Does that make sense? Aquifers and groundwater, all that stuff is not my forte. To me, it's kind of hard to visualize. So if you see any good online images or graphics, sometimes to me, I'm a visual learner, so it helps me to understand the process and kind of see how it's all laid out underwater or under the ground. But if you take a walk today and you see water, you might run into some water along the surface, and so you'll be looking at the water table, and right below that will be the unconfined aquifer. So, all right, so you guys have already rattled off a lot of these answers, but the different things that can affect water quality, it runs the gamut. There's so many things. Think of all the meteorological factors, like these things at the top. What kind of precipitation? Is it rain or snow? How heavy is the rain falling? How long is it falling for? How much fell? Think about the March 2010 rainfall event that everyone talks about, all that flooding. That was an intense amount of rain in a pretty short amount of time and a ton of rain. You can imagine the damage that that would do as far as erosion, stirring up sediment, essentially bringing pollutants into the waterways, whereas if you had kind of a gentle rain that didn't last that long, you wouldn't expect to have the same result. So intensity of the rainfall, how much and how long it lasts can all impact water quality. Your land use. If you have a big cleared field with no trees on it and it pours rain, what's going to happen with all that soil and dirt, or some of it? Yeah, you're going to have erosion, so you're going to have a lot of sediment in the water. That's going to affect water clarity, which can affect water quality. If it's very cloudy water, some animals may not be able to receive the sunlight they need, or the plants won't be able to receive the sunlight they need. So land use type, if you have a big forested area or an area with lots of grasses and vegetation that can absorb the rainfall, that can be beneficial. Let's see, elevation, topography, the slope. If you have a very steep slope and it rains, everything will wash down a lot easier versus a nice gradual slope. So all these things can be taken into consideration. Other things that can affect water quality and determine what species can live there or not are things like dissolved oxygen. Water temperature, as you increase your water temperature, your dissolved oxygen goes up or down. Anybody know? The warmer your water temperature, do you have more or less oxygen? Less oxygen, right. So that's why, especially when we get very warm temperatures in the summer, you'll often hear about fish kills or fish die-offs. Your water temperature got so warm that it was holding less oxygen and there wasn't enough to support the life in the water. So you have these big fish die-offs. That can happen for a number of reasons, but a lot of times it happens in warmer weather when the water temperature is up and it holds less oxygen. pH, the acidity of the water can have a big impact. In the marine world, that makes a big difference with, we're dealing with climate change and ocean acidification, and we're seeing more acid in our water. It's slightly more acidic, and so that affects things that need to make shells, because the acid is not good for shell-bearing animals like clams and oysters. So pH can have a huge effect on water quality and the critters that live in there. And then, we already talked about pesticides, fertilizers, chemicals. All those things obviously have a huge impact, and they all come from different places. So this map is really cool because it just kind of shows everything on one map, and then even talks about everything we talked about. So road salt, oil leaks, automobiles, septic systems are huge, or sewage treatment centers are usually can be a cause of poor water quality. If there's a raw sewage leak flowing into the bay or the river. So if you have poor sewage systems, septic systems that aren't fully contained or they're leaking, you've got a lot of excess nutrients getting into the water. Fertilizer, livestock waste, a lot of use of pet waste, that's a big one. May not seem like a big deal, but when you add up the number of dogs that are in Rhode Island and the number of people that leave the dog waste right on the side of the road or of the path, and then it runs all the dog waste ends up in the water. That's a lot of bacteria. It's a lot of extra nutrients going into the water. So this is a really great map, and I think aren't we gonna make this available, this PowerPoint?
I believe
Or some of these
so. I
slides.
was going to be able to make some.
So it's got the water cycle on it too, transpiration, precipitation, evap, and then a lot of these sources of pollution. So one of the other big ones too, which we don't see a lot of here, but it definitely is happening, but it's generally hidden. A lot of toxic waste from things like barrels that have been buried, or old factories, or they had to do something with their toxic waste, and a lot of them are in barrels that are buried underground that are could potentially leak at some point, and you could have leaching out into the soil and into the groundwater, contamination from that as well. So that's a really good graphic to keep in mind. Do we want to do that super quick?
Yes. Can we have everybody try and gather around? You just want to, it's sometimes easier just to kind of visualize and see that things are kind of where they go, right? Thank you. All right, so if you can gather around, this is just kind of a visual imagery. We do focus on a lot of the tests on watersheds and what happens with water. Water quality is huge because we all need good quality water. So
Oh, gosh. Yeah, you know more where these things
All right,
all belong. Here, I'll start sprinkling.
We have a whole bunch of stuff. Now, we could do this. I'm sure you guys have done this before. But basically, we have, as the model, topography plays a huge role in the watershed cycle. So this would be the watershed itself. Here's the mountain that goes down. Now, if anything happened over here, that water particle would be in a whole different watershed area. So we have some agriculture. So we have some soil over here.
No, I'm going to add a little bit more.
All right.
Loose soil. It's been farmed. There's nothing holding it
Yep.
in place.
All right. And then let's see what we're going to do some garbage right around here. Oh, no, we're
This one?
yeah, let's do that one.
A
We're
little
gonna
bit
do
trash.
some trash around.
Very,
If you look at our highways, right, there's
Every
tons of
exit
trash.
ramp is disgusting.
It's awful.
So embarrassing.
It
What
is
wrong?
awful.
Yeah.
Awful, absolutely awful. There's some these would represent irrigation of like our turf farms. We don't have the circular irrigation. That's usually more out west. But right here is where you would have runoff from irrigation and stuff. Communities. And then we have this. And we're not going through everything over here. But this is a factory with an output. Now, can anybody tell me the difference? There's point source pollution, and then there's non-point source pollution. Anybody tell me the difference? Yes.
Point source pollution is very localized to one place. You can identify it. So for instance, if one factory is outputting pollutants or chemicals or something, then it's often very severe in that region. You can also identify where it is and then act to stop it. Non-point source pollution, on the other hand, comes from a broad range of things. And so if you have a general trend of, say, pet waste or fertilizer over a large area, then you can't localize it to a certain place. So it's going to be less intense in like a small area, but it's also going to be more of like an epidemic issue.
So this oil, we're going to do that. This is oil, and that's going to be non-point source because it's all over the place. It's all on the roads and stuff like that. So
Yeah, like think of, pet waste. And
Yeah.
all those things are considered non-point. But if you drive into Providence, you can very easily see all the point source pollution. You can see the factories emitting their chemicals. And if you had, if the wastewater treatment center failed or overflowed during a heavy rainstorm and that raw sewage went out, point source pollution, you can directly point to it and watch it going in. But you're right, those are fixable. Those are things that we can actually do something about versus non-point, which is the majority of the issues of our water quality in the Bay are non-point source pollution. It's just coming from everywhere, and it's hard to identify and it's hard to stop.
all right. So who wants to volunteer? All right, we'll have you volunteer. You'll be our rainstorm.
We're going to add a little more debris.
And what we're going to have you do is we're going to have you maybe do a sprinkle. It's just going to sprinkle today. So is everyone that has that's a stream? So there's a spray. So we're going to spray. This is just going to be a nice little afternoon shower. All right. So start just like little afternoon shower all over the place. So what do you guys think as it's just kind of spraying around just a little bit? Is it really kind of affecting anything right now?
I thought it was just beating up.
Some of the ones up on that side are sort of moving, but not really.
Right. So they're probably a little bit higher up in elevation, so they're going to have more of a tendency to roll downhill a little bit. All right, so now we're going to switch it over to stream. This is a big old powerful storm, so
Summer thunderstorm when all of a sudden
yes,
it's a deluge.
it's like all
This is actually
deluge.
waste.
And try and have it comes to
Those aren't doing too
And
well.
if rain actually came down this way, like
well, sometimes it does. Sometimes it comes down at that slant that really, goes through. But as you can see, so there's pollution already starting to enter that Bay Area already. And then coming into the streams. You guys are nice and wet right there. You can draw rain gear.
It's just really to drive that point home that all
there we
this
go.
stuff is going to one common outlet, one common place is collecting
Cows?
all of this material.
The cows have been killed by the flood.
They are now drowned.
Yep.
And what's funny is that, you know, he's doing it so that he can get rainstorm into a different watershed. That helps too. That means it doesn't get into your lakes and streams, so have it go into a different watershed. So you guys get the point, right?
So what would be one of the benefits to, you know, farm fields, a lot of time, you know, they're less fallow, they're not being used anymore. What are one of the benefits to letting them grow back into, you know, kind of a forested area or something like that? What do you think?
All the nutrients will come back a little bit more and the soil won't be all loose and be scattered around.
Yep. Yeah, exactly. It holds the soil in place. You won't have all that erosion, all that sediment. What else?
Well, if you don't plant the fields, then there's a large risk of erosion, so you're actually going to be losing soil. On the other hand, if you try and plant something like legumes, then you can try and bring nitrogen back into the soil, and you can actually have a positive change.
Yeah, exactly. And if it was a farm you didn't want to even farm anymore, and you let it go back to forests. Forests are great carbon sinks. They store a ton of carbon, and that's taking it out of the atmosphere and holding it somewhere else. So that's always a really good benefit as well. When you clear areas and you cut trees down, you're releasing a lot of carbon back into the atmosphere that was once taken out of it. And so with climate change at the forefront, that's a huge thing as well. No,
This rain's over. And not to interrupt, but the other thing is, you know, even if you're keeping that farmland, just putting that buffer zone in front to avoid that runoff and stuff like that, that is a best management practice. So just having that buffer zone to prevent the stuff going into the bay and different waterways.
Yeah, if you were alongside a stream or a creek and you had that farm there, you know, just planting some kind of winter rye or a grass or something at all to slow down the running off of that soil is imperative. So, but the big picture is just the watershed. You know, everything we do within that watershed is going to impact that water quality, and that could impact recreation. It can impact tourism, and then all of that goes right into impacting our economy as well. So all of it's connected, and I think that's the big thing to take away from these watersheds is the idea of the watershed is that it's all connected. It's all directly related to things we do every day or things our family members do, and you have an impact. You have the ability to make positive impact. It really is that simple. So just things to consider and keep in mind. So yeah. Anything else you want to cover with that? I think we're good on time.
I think that's good.
Okay.
All right.
Perfect.
Wow.
Okay, that's it.
It's almost like we planned that.
I know.
All right.
Have a seat,
So
I
you
guess.
guys sit on down. We know what causes pollution, what possibly we can do to prevent pollution, but how do we know if a water system is polluted? How do we know? Like, yes.
By testing it.
By testing it, exactly. I was going to go through like this big old thing that if it's clear water doesn't mean that it's good water. So you already got it.
Many species can be biotic indicators of water quality. It's amphibians and macroinvertebrates can be studied.
Excellent. Wow. You guys should be up here. I mean, like, yeah, that just like tells an hour right there. No. But no, seriously, but that's excellent. So basically, we have two different types of testing, of water testing that we do commonly. And one of the biggest ways, one of the easiest, most concrete, I should say the most concrete way, is to actually stick a probe in there, get the probe for oxygen, get temperature, get stream flow, get...
I can turn it off. Give me a hand.
All right. So what we're going to do is we've set up, how many different teams do we have? Just have the advisor raise your hand.
You don't know her.
So we have about 5 teams?
Well, 5 advisors.
5 advisors, okay, how about teams that are present?
3 teams.
3 teams?
We've got 2 present.
2 present, 3. I'm just trying to think of the best way to separate you guys up. We have 4 test kits, 4 testing stations. So I'm just trying to figure out the best way to separate that out.
For one? So we have 5 schools basically.
Okay, so we'll go with school. We have 5 schools?
We have Coventry, we have Narragansett, we have Beacon, we have Situate, we have Compass, we have Wheeler, and that's it.
We have 3.
Green.
So we have 7 schools.
Alright, so we have 7 schools. Alright, so.
Who's here from Green? We only have 1 person from Green? So they can join one of the other schools. Work together.
So, basically, what we're going to do is, we are going to separate into 4 different groups. So, we can figure that out.
Yeah.
Yep, so, alright, so we're going to separate into 4 different groups. And we brought a couple of different testing things, and in the past, we've only done macroinvertebrate sampling or biological monitoring, which we're going to cover a little bit later on. I have a fun little group activity there, a big old competition. But right now, what we're going to do is we're just going to familiarize you with some of the tests that we have going on today. So, with a grant from TU, we're able to get some testing kits. So, what first thing that we're going to do is test for pH. What is pH? Yes. Acidity in the water. Acidity in the water. So, what's the range on that? Yeah.
pH ranges from 1 to 14. 14 is the most basic, 1 is the most acidic, and that's determined by the amount of hydrogen ions in the water.
Excellent, excellent. And now, the other question I have is, what's the general range that most fish species would be able to survive in our lakes and streams? General range, yes.
Like 7 is the best.
Yeah, 7 is the best, it's the most neutral, but fish species can go from 6.5 to anywhere 8. I'm talking trout, salmon, because that's what I deal with. But there, some species, such as brook trout, can handle waters that are a little bit more acidic, a little bit towards a 6.0 to 6.5 range, whereas rainbow trout, same type of, in the same family, they need definite 6.5 to 8 in order to survive. So even different fish species can survive at different rates. The other thing is, how do we get our oxygen?
That's the workshop, I think. Situate. It's on the online mapping stuff.
It constitutes 20% of the air.
Exactly. So we breathe the air in. How do fish get their oxygen?
Do you have any questions?
Yes.
The water flows over their gills and then dissolves oxygen from the water.
Right. So there's, what did you say, 20% of oxygen in the air. In streams and stuff, we're talking, there is, at best now, 8 to 10 parts per million of oxygen. That's significantly lower. So those skills have to be very, very efficient. Even in the macroinvertebrates, there are macroinvertebrates that need that. So dissolved oxygen is extremely important, especially with the fact that there's no tornado hitting us, right? Okay. Just want to make sure. No severe storms. All right. So anyway, with dissolved oxygen, we know that at between 3 and 5 parts per million for fish species, they don't survive very well. As opposed to after 5, they're more likely to reproduce, which is really what we want them to do. So we are going to test our streams for oxygen. And this is going to be very important when it comes to test time. Because if you're not familiar with these tests and not familiar with the equipment that you're going to need and use, you probably won't, you'll take a lot of time trying to figure it out. And that's what this is for, so that you're able to get right to your test, figure out what your group is going to do, kind of get everything where it needs to be. We also have thermometers at each station. And basically when you take a temperature, it's really easy, right? But what you want to do is you want to put your thermometer in and you want to swirl it around. And you don't want to just immediately take it up. You want the temperature to actually register. So you want to go for a good minute in the water, kind of swirling it up. And not at the surface, but
right in the middle to the bottom. So that's how you're to properly take the temperature of the screen. And then I also have a phosphate, so I'm going to give you guys about 20 minutes to figure it all out. There is a lot of information in the dissolved oxygen. With dissolved oxygen, when you do take your sample, you do want to make sure this is a water sampling bottle. It's very important that you put it all the way into the water and cap it completely full under the water. Why is that?
You don't get more oxygen in.
Exactly. So it's that air-water interface. So we want to make sure to get an accurate an accurate DO. Make sure you completely fill this and then cap it underneath the water, making sure that no air bubbles are in. And then you'll have solutions that will fix that oxygen in there, and then you'll be able to play around with it. So I want you guys we'll break up into the 4 groups and go from there. So Pete, I'm going to have you help me with that.
Okay.
So 2 groups are going to be at this bucket, and 2 groups are there, and I will open up the phosphate kit. Once you're done with the DO, I'll have you do the phosphate.